Yvain Bruned, who will talk about renormalization in regularity structures, part 2.
So I would like first to thank the organizer for this workshop and also the Institute for this nice program. So this talk will be the second part of the talk given by AJ yesterday. And okay, we'll continue this description or how to renormalize, or what is renormalization in reality structures. And the main idea is that what I will present in that talk is mostly algebraic structure. I mean, when you have a lot of computations coming out from these singular SPDEs, or to organize them and to have the good structure for treating very complex examples. So the main example you have to that you will have to have in mind for the talk is this geometric KPZ equation. So seen as a most natural stochastic evolution on a loop space. So here you have the equation. So here you have the Laplacian part, and then you have two ill-defined products. So you have this quadratic term coming from, we can see also in the KPZ equation, and you have also this stochastic product. Here the Xi will be space-time independent white noises, and the gamma will be Christoffel symbols, and the sigma has some collection of smooth vector fields on the manifold. So why I choose this example? Because in comparison to 543, I mean, you will not have only power of the solution, but also derivative of the solution here. So it really makes a difference in terms of the representation with the trees, in the sense that you have more decorations around. And also, when you start to solve this equation by hand, doing some perturbative expansion with trees, it turned out to be very complicated in the sense that you have more than 40 terms to treat. So this is, I would say, the starting point for if you want to automatize this theory. So of course, in this question, where you have the problem, of course, will be to give meaning to these products here, ill-defined products. And in order to give meaning to these ill-defined products, you have to subtract some renormalization term here. And in this talk, I would like to give you what are the good description for the renormalization terms, and also the constraint you have on them if you want such, or if you want some properties on the solution. So these are the three, some questions you can address on this equation. So of course, this is the first point. We want to give a meaning to this singular SPDE. And this is the same as for 543. So most of the talk will be in this around this question. So I will present how to generate the trees, how to renormalize them, what are the main algebraic structures. And then there are two other questions which are more related to the symmetry properties. The first one, that you want some notion of solution which is covariant under change of coordinates. And the third one here, it's a kind of isometry. You want your solution depending on the law of the solution depending only on the metric and not on the choice of the vector fields. So for both of these three equations, you need very good algebraic structures. And most of the talk, as I say, will focus on this point. And at the very last end, I will try to explain how you can answer these two questions. Okay, so first, before starting with generalized KPZ itself, let's start with just the KPZ equations and try to explain a bit the perturbative expansion with trees, a bit like for 543. And as we've seen in the talks before, is that if you want to look at the solution of these KPZ equations, your first approximation would be to think of look at the solution of the linear equation, the stochastic heat equation. And here you have an explicit representations in terms of this process. So just take the convolution of your heat kernel with your space-time white noise. You know also the space-time regularity. And what you do is that you want to do some perturbative expansion, that you want to see U is very close to V, and plus some remainder. And this remainder will have a better regularity than the solution of the linear part of the stochastic heat equation. And so when you do your expansions, first you will have some other stochastic term popping out. And a good way to represent them is to use what I call here decorated trees. So here, so you have some combinatorial objects, and here you have some map, bold face pi. And this map, you can see it as a rule which will interpret these combinatorial objects as analytical objects. For instance, here I have a dot, I have this dot, and this node here will be my space-time white noise. If I add a new root, and if I draw a line here, a blue line between this dot and this dot below, this will be the convolution of my heat kernel with my space-time white noise. And that's the reason why I choose the Capet equation, that you have two different lines here, one blue and here this brown, and this will be for the derivative of the heat kernel. So you have your noise, and then you have this derivative of the heat kernels. You can take product, here you have a product, so this is that tree, and this is just the square of the term before. And if you want, you can go on with the construction of your tree. You can apply some convolution here at the bottom, so you extend your tree in this way, and you obtain that term. So this is the solution of the stochastic heat equation, the linear part here, is given by the interpretation of that tree. So this is the combinatorial objects, and then you want also to associate to each combinatorial objects a degree, a scalar, with which measure how singular these objects are. Once I have interpreted with my bold face pis, I want to know what should be roughly their singularity in terms of distribution. So that's why we associate to each of these three scalar, and the scalar will be a degree. So first here for my dot, I associate here which would be my space-time regularity of my space-time white noise. So here you have to think that kappa is small, is very small here, so you are just below -3/2 in terms of space-time regularity. Then when for the solution of the stochastic heat equation, the space-time regularity will be given by 1/2 minus kappa, so you have a +2 from the previous term given by the Schroeder estimate of the heat kernel when you convolve with the heat kernel. And when you take derivatives here, of course you go -1, so you have a -1/2 minus kappa. Taking the product, you take the sum of the previous one, you got -1 -2 kappa. So these are the degrees that AJ is presenting at the level of the tree for 543. And here, if you take the degree of that term, you just do a +2 here by adding this h, so you have 1 -2 kappa. So the only difference with 543 is that I have two different type of ages, like this blue one and brown, for derivative of the solution, or the derivative of the heat kernel, or the heat kernel itself. So, and then, you have this bunch of trees, you have this degree, and what you want to know is that, you have to care about the trees which are of negative degree, with the one which are singular, and the one also which have encode this singular product you have at the level of the equation. So using this formalism of trees, you can, for instance, if you do your perturbative expansion, you are able to write down an equation for the remainder. So you have this W, you have this remainder, and you have replaced your space-time white noise with something which is here with this stochastic process. And this stochastic process is less singular than the space-time white noise, so in the sense that it's much better here than the original equations. And what you do, you go on, you start, so the second term in the expansion is this one, and then you have another remainder, and you start to go on your expansions. Of course, this perturbative expansion is not enough for solving the equation, that if you want to solve the remainder, you need to work on a certain space of Rathpass, or here it will be regularity structures. But here you have the structure of the term that at the very end you need to control if you want to give a meaning to your equations. Now I would like to, this was like end computation. You expand, you start with the solution of the stochastic heat equation, then you expand the next term, and then you go on. But what you can do is that you can formalize this. You can put rules and say how you can generate all that trees. because if you have 40 terms, you will not start doing this computation and for these 40 terms. So what you can do is that, okay, let's look what I have in my equation. So you look basically at the right-hand side. So you look what I call here, what are here these non-linearities on the right-hand side. So what I have on my right-hand side? Okay, I can start with my noise. Okay, so my noise is here in my set of trees. Then I have a product. Okay, this is a product of dxu square here, and this product actually, when you expand, you do your expansion in terms of trees, gives you rise to different ways of constructing your trees. So the natural way is what we did is that here I can, if I have constructed tree tau1 and tau2, I can just plug in like this. So here will be my derivative with my kernel, convolution with what I have on the top, and I can take that product, and this producing me a new tree. Or if I want one of the branch here, I can represent one of the dxu plus some x, so I can have these terms, or I can have just polynomials. So when here I have a precise characterization of my trees. So if I look of trees which are in this set T, I just need to look at each node of that tree, and this node should check some kind of this identity. So I have characterized what are the incoming edge to my node, okay, which are the rules, and these come from the products I have on my right-hand side. So then, okay, let's switch to another equation. Imagine that you have this on the right-hand side, which appears at for the geometry KPZ. Then what you do, okay, here you don't have a polynomial. Here it's a very non-linearity, and what you do, you have in your mind is that you replace this non-linearity by any kind of power of u, and this gives you that rules. Okay, so you have your space-time white noise here, and you take product with as much as you can here of branches which represent u, okay, which are coming from u. And you have also polynomials here, okay, and this gives you like an infinite number of rules for building your tree. But of course, what this is, the one which are important is this one, because you know that this one can be very singular. So here you just allow 2. If you allow 3, I mean your tree will you will not be able to prove the convergence of that tree and or to control to have bounds on that tree. So these are the trees which are on the right-hand side, okay, which are generated by these perturbative expansions. And when I want to have an expression for my solution, what I do, I just take trees in this space T, and I just integrate them, or I convolute with my kernel. So I just add this blue line, okay, and it's like kind of a Taylor expansion of my solution. So I need also the polynomial to describe my solution. So if you just think of a C alpha order function, you will not have this term, but just the polynomial. And then what you do is that you have this kind of Taylor expansion of your solution, which is given by these trees, which are defined here. So among them, you have the classical polynomials. And now, of course, you need to, okay, the polynomials, you know how to recenter them. It will be y minus x power to the k. And then for that, the other trees, you need to recenter them by using what AJ presenting, what was this model. So here it's a renormalized model, so I have smooth out my noise, convolving with a modifier. And in these Taylor expansions, I know also very well which are the coefficients. So I can compute the coefficient from my equation. So I will show this at the very end of the talk. And I have some remainder which behave as some y minus x power to some degree. The degree, which is a degree, because here I will truncate my sum according to the degree. And for the KPZ equation, if we look back to what kind of expansion we have, now it's like a Taylor expansion. So I replace my ball phase path, which has been just a naive interpretation of my combinatorial objects, as this recentered objects. So just a clue, what is the procedure of recentering? Here you have it on just the solution of the linear equation. It just I subtract, I take the value of my ball phase pi here at y. So this is my convolution of my kernel with my modified noise. And then I subtract the value at the point x. And I expect this to behave well in y minus x power to the degree of the space-time regularity of that term. So of course here in this example it's very simple to know what you need to do for recentering, when the tree is very big, I mean, it's not, you need to perform some kind of renormalization procedure, and it's what we will see in the sequel. Okay, so now I will describe two renormalizations. One is what you have for recentering procedure, I mean to try to recenter these combinatorial objects. So this is given by the model, okay, you have this pi x, and then you have this map that AJ described in his talk, which allows you to change the point in which the element is centered. And of course you want this kind of bounds that for polynomials that's a tree here, this pi x of tau taken at y, you want the behavior around the point x power to the degree of the tree. And you have a structure behind this, that this map gamma xy, they belong to what we call here the structure group. And behind that, in order to define the structure group, you have alpha algebra for the structure group. On the other side, what I presented, okay, is just here you try to write down an expansion, a Taylor expansion for your solution. You recenter some combinatorial object to some analytical object. But of course, then you want the convergence. You want to renormalize the ill-defined product which appears at the level of your equation. So for that, you need a second renormalization, which we call a negative renormalization, which will be maps acting on these trees. And these maps actually will prepare the renormalization. As AJ mentioned in his previous talk, what we will do is that we will not do renormalization at the level of Feynman diagram, but we will do it at the level of this combinatorial object, at the level of the trees, before computing the covariance. And what you want to understand is that, okay, I define a renormalization map on my trees, a linear map on my trees, and I want to act also on the model. I don't want to break down this recentering operation at the level of the model. And so here I want to define what is a renormalized model. And then also what I want to get is the action onto the equation. I want to know what is a renormalized equation when I renormalize my model. So for constructing, for instance, this map, it will be an alpha algebra, so I will present it in the next slide. And if you want to understand what is the action onto the equation, you need to use another structure, which is a pretty structure, which will be kind of the dual of what we did for this alpha algebra. And so the aim or the target, okay, when you look at these two renormalization, you want some compatibility. By compatibility, I mean that if you define what should be the simple formula for your renormalized model, this will be that one when you have decoupled the two. I mean, you first start by renormalizing your tree, and then you try to recenter them by applying your pi x. And so you want this to be the correct formula for your model, and it's also a nice formula which is very explicit. And this formula is untrue if you just keep it on the level of that tree, so you will need a bigger space to also explain which are the issues for getting these co-interactions. So, okay, you are not specialists with alpha algebra, so I will try to start with a very simple example to explain what is recentering. So let's start with a C-infinity function, okay, phi. And what I want to do, I want to compute its Taylor remainder. So I just look at this Taylor remainder around the point 0. So I subtract here up to 1 order, and I have some remainder. And now I want to abstract this. I want to explain this, or you compute this Taylor remainder, or you do these Taylor expansions at the level of trees. So the simple encoding we have here is that my map phi, I will just encode like this, okay? Just an edge of this kind. So think of the hit kernel for the case of SPDEs. And then what I do is that you have to think in your mind that I have some here. I will be I have a map which will be this map delta plus, which will go from the tree into the tree tensor the trees, and you have to think that on the right this tree will be interpreted at the point 0, and on the left it would be at the point y. Okay. So for instance, the first term here would be here. So I just take my tree and I put this tree here on the left. Then I change point, okay? I just not here y, I'm here 0. So I have the tree which is on the right. And then, of course, I can play with decoration, or what I say, I can play with decorations. Here I will have my derivative of my function phi, and I have my polynomial part, okay, which I will put here with a dot. I will have one thing that I have here, this x. So actually, if you look, and if you want, you can go on. If you want better order or better approximation, you can go on depending on which regularity you have put on your file. So if you just, I would say, if you just remove this part when you play with decoration, I mean, you just subtract the phi of 0, I mean, just that part. Okay, here, for those who know a bit of algebra, this part is just a primitive part. And what we did here is kind of a cutting procedure, is that I have started with a tree here, and I have cut that edge. And what I have cut here, I have put it on the right. So what you can think is that, okay, this part, if you just remove the play with decoration, this cutting procedure is known as Kohn-Kreimer coproduct, and is really well understood. But then when you play with decoration, it starts to be because you want to encode this Taylor renormalization. And another remark is that you can think of this coproduct as some perturbative version, a deformed version of the Kohn-Kreimer, okay? You deform your Kohn-Kreimer by adding this game on the decorations in the sense that you want to go to next order. I mean, you just want to subtract just the value of phi at 0, but you want to subtract the higher order level, okay? So it just, you deform the coproduct by playing with decorations. So this is like the basic stone for recentering. Okay, then there is another ingredient, which is also why you are which is not appearing in Kohn-Kreimer, is that you have polynomials, okay? Polynomials everywhere in your trees at every node. So also you need to know how to recenter monomials. So now if you think of T, okay, just the polynomials, and polynomials, I mean that you have just a node decorated by K, then you have a classical coproduct on them, okay? So you can, so if this will be the x will be here primitive, and by multiplicativity you can extend to any power. Okay, here I describe for those who are familiar, which would be the in the framework of algebra, the co-unit, the antipode for computing the inverse. But I think the most interesting part is the last one, is that in that case, when you look at monomials, it's really easy to formulate what is the structure group for regularity structure. And in that case, this structure group will be isomorphic to R, and you just translate here x to some scalar g of x. So this is a difference. So you have this cutting edge procedure. You have this recentering of monomials here given in that example. So these are the two tools for computing your pi x. And then, okay, then it's another renormalization here. Here I'm not interested of having some small behavior, around a point x. Here what I want is to cure divergence or renormalize some ill-defined integral. So here I've just write down here a renormalized integral. So here, K, you think of its kernel of some kernel which is singular on the diagonal. And here I have a convolution of modifiers, and you have to think that this will converge to a direct, so y will be extremely close to z, and you have some blow up on this kernel. So what you do here, you want to renormalize your test function in order to cure this blow up, and for that you need, so this is phi your test function, and then you subtract Taylor expansion up to the order which is the singularity when y is close to z. So here I've write down the renormalized integral, but as for this Taylor expansion, we can express it at the level of trees or cutting edges. So here I write down what should be the term before taking the expectation. So here you have your space-time white noise, okay, product with the convolution of the kernel with what you have on the top. And okay, what I want to renormalize is what I take the expectation value, the expectation of that term, which will give me this singular part of my integral. And as before, okay, what I do is that I put a Taylor expansion, so I will cut the edge here, this phi, here I put it on the right, and this is where I perform my Taylor expansion, okay? So here I will cut it once, I cut it, and then here I do the same game of the decorations, putting a derivative on the phi, and putting an x on the node where the edge was originally located in the tree. And if you want an analog of this coproduct, this is also a well-known coproduct. It's extraction contraction. So what I did here, I have extracted this subtree. And the way why I've chosen this subtree, because this subtree is of negative degree. We can compute its degree according to the rules I presented before. And I will stop my Taylor renormalization up when my tree here, when I add x, which increase the degree of this tree, is positive. So it's extraction contraction, but as before, you have a deformation. I mean, you play with decorations. Okay, so the structure just extracts sub-negative tree, then you play with decoration by inserting x here inside my tree and taking derivatives on the edge. So if you think of it, it's actually is like the combinatorial structure, this cutting coproduct and this extraction contraction coproduct are just at the level of the combinatorics of these trees. And then you have a second layer because you want to encode or the renormalization of your singularities, or you want to subtract next order. You have to incorporate this Taylor expansion at the level of the combinatorics. Okay, so before presenting the main results on this coproduct, I would like to just stress out which are the structure behind. So first, okay, here this calligraphic T, you have to think of it as the linear span of the trees I presented before. These are the trees which appears when you perform your perturbative expansion on the right-hand side of your equation. This is not an algebra, okay? You cannot multiply the trees, because if you do that, it means that you are creating maybe a new product in your equation, so you have some risk. This is not an algebra. So then you have another space, which will be the space of 3t plus. So the space of 3t plus, okay, I put here positive degree respecting what I call this product, which is a joint root product. So I have two trees here, and I try to multiply them and obtain that tree when I merge the two roots. So I will ask that every tree, okay, every branch coming out from the root to be of positive degree. So you have to imagine that T plus is a space obtaining when you do your cuttings. You cut different edges, so you obtain different branches, and then you collect them to a single tree. So here the product is free, okay, in the sense that you have a product here on T plus, and you have no constraint at the root. So you can take as much product you want, because these are positive branches, and at the end they will be interpreted as functions, so they are not ill-defined distributions, so you can take products of them. And then the third space, this will be the space of your renormalized constant, if you want. There will be the span of negative decorated forest. So I've written down here a negative decorated forest. And you have to think that every tree in this forest is of negative degree. So these are the trees or the divergences you have extracted from your original term in T. And these are all of negative degree, so these will be the renormalization constant you need to subtract with some counterterms to make sense of your stochastic process. So these are the three spaces. And then, okay, here I just show the action on the shape. It's what we've seen, that the first one we saw, it was this delta plus when I cut edges. So the edges are in blue. So I cutted them, and then here I take the product of them, so I cut the edge here. And above you have this extraction contraction coproduct, this delta minus, extracting the tree with negative degree here, put them on the right, and then shrinking them on the right here. So here I've put also blue edges here, both in the both core product, just to stress out that you do some Taylor expansions. That's like it's not only this, but you have a deformed version which will place with decoration here. You will put Taylor expansions on these edges and also at this level. And what we proved in this paper, that algebraic renormalisation paper with Martinera and Lorenzo Zambotti, is that the structure you have just as a combinatorial object, you go obtain the same results for when you play with decoration, when you incorporate Taylor expansion at the level of the algebra. In the sense that you have off algebra for T plus delta plus, you will act also on T. This action will give you the structure group, which allows you to change the point of your recentering monomials. You have the same for T minus, that you have off algebra, and you will act on T. This action will be given by the renormalization group. Now there is a last point, which was not really obvious when we start to work on these two renormalizations, is that you want co-interactions. Okay, so here I will explain what is co-interactions. So you want to perform the two renormalizations at the same time. This will be your renormalized model. So one renormalization is cutting edges. So here I have two edges, E1 and E2. And the other one is extracting subtrees. Okay, so I have subtrees here, TO1 and TO2. Okay, and then here I have some compatibility that my edge, these are disjoint, my edge is not inside the tree I extracted. So when you do that, you can do it in different orders. You can first cutting, then extract, or first extract and then cutting. And you want them to commute. You want the operation to commute. If you don't have any game with decorations, it's kind of obvious. Okay, you have to check if you can revert, but it doesn't seem a big issue. But now what happens if you play with decorations? So here I represent what I did. So here I started by first extract. So I extract my two trees. So I shrink here on the right. And then here I do the cutting. I cut here, and I have my tree on the right. So the problem is that when I play with decorations, here, when I will cut this edge, the level or the length of the Taylor expansions depends on what I have above. Okay, so what I have above is that tree. So whereas here, if I start to do the cut, I have something different. I have that tree, which is singular because you have this negative part. So the length of the Taylor expansion will not be the same if you do the operation in different order. So here what I did, I just cut the edge first. I cut them. So I have in the cutting I've taken into account that I have this negative subtree, and then I extracting the different parts. And if I multiply these two trees together, normally I obtain this picture. But the difference is that here, at this level of the level of this edge, the lengths of the Taylor expansion are different. So this, in that sense, you will not obtain a co-interaction, or you cannot revert. You cannot commute the two renormalizations. So in order to do that, you need to keep track about one information. What is missing when you do your Taylor expansions? What is misleading for you? What is misleading is when you compute the Taylor expansion, you take into account the tree above, but you forget that there was some singular subtree inside. You forget that there was this structure before. So in order to keep track of that, you need to add some reminder. So if, for instance, if I extract that tree, I will take a reminder saying that I have something of degree τ1 at this node. So when I will perform my Taylor expansion on this part, I will take into account this degree, which will shorten my Taylor expansions, and it will be exactly the same if I first start to do the cut. So if we put this extended, we call it extended decorations, which are just reminder of what has been done by one renormalization, and then the second renormalization can take into account this degree, then you are able to obtain this nice co-interaction and this nice formula I presented before. So this can be summarized that you have this nice formula for the renormalized model, and you have two groups. Okay, the first one is the one used for the structure group. So these are characters for the tree product, joint root product. Here you have characters for the forest product. And then from these two groups, you are able to construct the map M. So from the character G, which are in R and G minus. And you're also allowed to pick up one character for the recentering, for constructing your pi z. And if you work in this framework of extended decoration, which are just keeping track of what has been done by one renormalization, you are able to write down this nice formula for the renormalized model. So this was kind of a preparation, if you want, for organizing all this renormalization, I mean cutting, extracting, and this was the main formula, if you want, for proving the convergence, which has been done in the paper of AJ and Martin in the sequel. And so this gives you the renormalized model. But then, of course, okay, you have your Taylor expansion of your solution with this renormalized model, but then you may ask, okay, I know what I need to do at the level of my model, but what happened at the level of the equation? Or this renormalization or this map M will act on the renormalization. So for that, okay, this was this paper with AJ Sandra and Ilya Chevirev and Martin Herrer, when we managed to prove that if you start with this renormalized model, you are able to derive the action at the level of the equation. So if we go back to our example, so here you have your generalized KPZ equations, then you are able to compute here the counter terms. And these counter terms here you have two parts. So here you have these renormalization constants, which are actually you have to choose one element in your renormalization group among these characters on the forest. So you have one canonical choice, which we call the BPHZ character. So this BPHZ character, you have here, okay, you have here some maps. So this map, you have to see it, this A minus tilde, as something performing extraction, but in a recursive way, in the sense that you want to deal also with subdivergences. So you apply this map on your tau, then you interpret them, all the elements you have here, and then you take the expected value. And this gives you the counter terms you need for, you have at the level of the equation. Then you have another component here, which are the coefficient. Okay, you are an explicit. You have also an explicit representation of the coefficient. So in order to derive that, so before I presenting procedure which were cutting edge or extracting trees, you need to deal with another structure which is close to the, can be seen as a dual as we've seen. We need to deal with pretty structure, which was the key point for deriving this renormalized equation. And of course, when you look at terms like that, you have also other questions. I mean, for the symmetries properties I presented before, you want to be able to understand what are the nature of these terms, okay? Because here you have some choices, okay? You can change the character a bit. I mean, you are able to choose another character. So you want to know which are the canonical or in what kind of solution I want. I mean, because I can tune this renormalization constants. So if I want to satisfy some symmetry property, I have some room for changing them, and I need to understand the structure of these counter terms. Okay, first we call you what is a pretty structure. So this is kind of the opposite. So we've seen that you have a tree, you cut edges. Now what you do is grafting. Okay. So for instance, I have a node here, and I will graft according to this edge. Means that I can join this tree with this edge to the root, and I have two choices here I can do on the top. So here I can do this also. And I will have two grafting operator because I have two type of edges. I have K, my ith kernel, but I have also the derivative of the ith kernel. Okay, so that's why I have this brown edge. And so here this is exactly the same tree that just change the decoration of my grafting operator, and I will obtain two different trees. So what is nice with this grafting operator is that if you look at these generators, so you just here dot, so it will be just one, and here will be the generators corresponding to your noises. And if you equip these generators with these two grafting operator, you are able to generate the trees I presented before, the tree which appear on the right-hand side of your equations. So what is nice is that now you have like a decomposition of your trees into single step. Okay, so you have some generators, you have your generators, and you have some simple step or to construct these trees. And here I would just want to stress out that this decomposition was the main point for deriving the renormalized equation. It was first used in a work with myself, Ilya Chevirev, Peter Fritz, and Rosa Press for RAFPAS. So at the level of RAFPAS, these grafting operators are very simple. And it was shown that it was easy in that case to derive the renormalized equations. And then using this simple idea, or to decompose our trees, we were able to treat the case of singular SPDEs. And then it was not the end of the story. Is that this 3D structure, which is very natural, has an impact of how you want to compute these symmetry properties I presented before. In the sense that they are not only useful for deriving the renormalized equations, but they can give you nice properties or what kind of character you need to choose or what should be the correct notion of your solution for the generalized KPZ equation. So for that, first I would like to explain how you can compute the coefficient which appears on the right-hand side of the equation. So what you use is really this 3D structure. So first you define this map at the level of the generators. So here you have to think of this map as a map with a variable x, which here you have to represent x will be then substituted by the solution. And then you have a bunch of here variables v1, so you have to think of abstract variables. This would be for dx of u, of the derivative of the solution. And so the idea is that when you have some grafting according to one grafting operator, you take derivatives according to x, which means derivative according to u. Okay? And then the same, if you graft with this brown edge, you have derivative according to the derivative of the solution. So this gives you a very concrete way of computing these coefficients. And also, if you want to act on this coefficient with some renormalization map, you just need to define your actions on the generators of the trees, and then you say that you want to have some morphism property for this grafting operator. So below, if you want, I've given some examples, or when you apply this rule or you compute these coefficients, and you've seen that you obtain at the end polynomials in terms of the sigma, the derivatives of the sigma, and you have also derivatives of the gamma. And so now what happened is that you know that on the right-hand side you have a finite number of trees, which are trees of negative degree, which are the ones which are singular. You have quite a lot of them, maybe around, for generalized KPZ, maybe above 50. You know that they have like this structure, and they will have 4 leaves, so there will be polynomials in sigma, derivatives of the gamma, and the derivative of the sigma. And now you want to understand what is happening if I act, for instance, on my sigma and my gamma with some smooth diffeomorphism. So you want to characterize, so you have to think of these spaces as subspaces of the main space, of this space of T minus, this tree of negative degree, which appears on the right-hand side. And you want to ask properties on this coefficient. So the first one, you want to have an x-actions with smooth diffeomorphism. So you act with your phi here on your coefficient, and you would just say that this is just same coefficient when I just act on the gamma and on the sigma. I want also my coefficient to not depend in law on the sigma, on the vector fields. So I want here an equality whatever sigma I take. And then if you want to combine both, you have some weak property where you combine here the two first property in some space of tree, we call it T both. So here it's like, okay, you start with the definitions that are like identities you want to check. And what is a game here is that you want to translate all of these relations into some combinatorial characterization. So you want to see this space like T geometric and the space of T satisfy this Ito condition. You want to characterize them as some kernels of some, okay, there will not be exactly morphism for this Preeley structure represented below, but some deform to Preeley, and there will be infinitesimal morphism. So what I say is that I will have some maps, we'll call phi geo and phi Ito, and this space, so there will be the kernel of these linear maps, and this linear maps will encode what should be the relation you should impose on your constant if you want to have the property I list, if you want this property list above, apply on the solution. You want your solution to be equivariant under diffeomorphism and also having this property. And here you would need to follow the path I presented before. You need to have this Preeley structure to define this infinitesimal Preeley morphism. And then you can understand what are the, or to characterize combinatorially these two spaces. And this was one results we have in this forthcoming paper with Franck Gabriel, Martin Herrer, and Lorenzo Zambotti, which tells you that one of the sub-results, when the technical lemma say you that you can say that this T-Bors is really the decomposition of the two, and we have a nice characterization for this space. So what I what to stress out here at the end of my talk is that it was very a long path in the sense that we started with trying to define or to give a meaning to this ill-defined to these singular SPDEs. So for that, we have seen that you have some expansions in terms of trees. So now we are able to characterize which are the trees which appears on the right-hand side, or you can renormalize them, or you can recenter them. Then you are able also to mix the two, I mean to do the two operations at the same time, and to see, we have seen that they can commute in a sense. And once you have this, you are able to construct a renormalized model. And this renormalized model, you are able also then to understand what is the action on the renormalization map on the renormalized equation. So you write down this renormalized equation. And then what are the parts which are not automatized or which are you need to work on is to understand if you want to pick up one solution, because your solution is parametrized by this renormalization group, and you want to have a good notion of solution. And then you need to analyze what are the symmetry properties you want. You want to translate them at the level of the combinatorial objects. And for that you need, of course, a good algebraic structure presented. And then you can work on at this level and try to derive nice property for the general KPZ equations, or what is the work which is work in progress with Martin Herrer and AJ Sandra and Aoshen on this Young-Mills, the dynamic of Young-Mills. So yeah, so you start with this renormalized equation and you work out what should be the symmetry properties using these nice structures for the counterterms. Thank you for your attention.
There is time for questions.
Are the algebraic constructions you do for in the case of negative renormalization will in any way related to the constructions of Kreiner and Kohn with the Hopf algebras?
Okay, the construction of Kohn-Kreimer, they will this tree will give you what are the hierarchy behind the subdivergences. So when you cut it, it's like you cut one subtree and then you have this hierarchy on the subtrees. I would say that this construction, or this really, because in the Kohn-Kreimer setup, I mean the age is just to say that this tree is included in one diagram. So in the sense there it's not really physical, okay, in the sense. Whereas here the age is its kernel. So it's really encode a stochastic process. So it's not a hierarchy among a forest or trees. It's really one stochastic process. So when I work on it, and the cutting here also have a different interpretation. It's not for proving the renormalization or the convergence of my stochastic process. It's to recenter the stochastic process. So it can be a bit misleading at this level that when you cut edge, I'm not trying to prove the convergence or renormalize, but I'm just trying to recenter.
I mean, in some models, like in gauge theories, you have anomalies. So the last result is, would it be able to detect this anomalies if there is one?
What do you mean by anomaly?
So like a symmetry which gets broken when you start to renormalize.
Oh yeah,
not
yeah.
enough constants.
Yeah, because of course, if you just apply this brute force renormalized model, you write down your equation, and if you just work with this BPHZ character, you may have been, you may break down all the symmetries you want for your equations. So then you need to you have a characterization of the symmetry you want on your equation, and it's not obvious that, that's why I'm saying that this theorem at the end, they are not obvious in the sense that you really need to find out if there is one solution or not, depending on the symmetries you ask on your equations. So if, for instance, you don't have these nice properties, I mean, in the sense that if it is not, maybe it's not, here it's possible, but maybe it's not possible to find a solution which satisfies the fact to be invariant under diffeomorphism. Maybe the constraint that we have on your renormalization constant that will give you no solution. And this is what you call anomaly, or? But okay, here I would say for generalized KPZ or this geometric KPZ, we didn't see any anomaly. It works well. So
yeah, I mean, but if you had the model where one would suspect there to be an anomaly, your formalism should be able to see it, right?
You will be able to see, yeah. I think using for instance, if there was an anomaly for geometric KPZ, normally we would have been able to see it, yeah.
Short question?
Yeah.
Short. It may not be a short question, in which case just...
Let me continue for lunch.
yeah. So somehow I've been seeing Hopf algebras coming into Kreimer's work, to your work, and I've continuously missed the point. What is it that you need to know about a Hopf algebra that's really useful?
Just that you are able to construct this group of characters. This is the one which parameterizes your renormalization map, and this is where you have you can choose which type of renormalization you want.
So it's like, well, okay,
I would say that the structure of algebra is just a way to organize your computations, because when you renormalize, you put many Taylor expansions
So there's no structural theorem of Hopf algebras that tells you something that you can use.
Yeah. I mean, you have some general theory of algebra which gives you nice property, and you can use that one. For instance, the Preely structure I presented is a generic structure which was there. I mean, it's like a dual of this cutting. You just graft trees on top of the other, and at the beginning, it was useful to investigate a bit the different structure they have of algebra and this. Because this was the path which leads us to write down the renormalized equation. So at the beginning, when I was thinking of this Preely structure, was just I would say not a toy, but just a way to nice structure. But then it really have an impact on how to derive this renormalized equation.
Okay, here's what I'm thinking. So once you have this coproduct,
Why don't you continue thinking at lunch?